All right, thank you, Maria. So yeah, I want to continue with the second part of these 4 lectures. So yesterday we constructed a sum of squares hierarchy for polynomial optimization. And today I want to do the dual of that. So I want to show how we can construct a moment hierarchy for polynomial optimization. And then, yes, as I've mentioned before, tomorrow we're going to apply this to point configurations. So we will see how the moment hierarchy relates to, for instance, the well-known Delsart linear programming band. And we will also see how we can use the sum of squares hierarchy that we discussed yesterday to compute this band. Okay, so just a quick recap what we did yesterday. So we looked at this polynomial optimization problem. So we minimize P of x where x lies in a semi-algebraic set, which is defined here. Then we said, okay, that's exactly the same as maximizing some constant where the polynomial minus the constant is non-negative on the set. And then we said, okay, we can see this as the cone of non-negative polynomials. And we can build inner approximating cones, right? Which are these truncated quadratic modules. So instead we require that P minus M lies in this truncated quadratic module. And this turns out to be a semi-definite program. So this is something we can solve on a computer. And then we discussed asymptotic convergence, which follows from Poutinar's theorem under some conditions. Yeah, so now I would like to continue with deriving the moment hierarchy, which is going to be, from a semi-definite programming perspective, the dual hierarchy. So first the definition, so P of S of Q is going to be the set of probability measures that are supported on this set S of Q. And then we see that instead of minimizing P of x over all points x in the semi-algebraic set, we can also minimize over these probability measures. So we minimize the integral over the semi-algebraic set of P of x against our probability measure. And then the optimization now is over all probability measures supported on the semi-algebraic set. And the idea is that, so say this polynomial optimization problem has a unique optimizer, then here the measure is really just going to be the Dirac point measure at that unique optimizer. If there are several global optimizers, then it's going to be some convex combination of the Dirac measures. And well, strictly, so proving in one direction is easy. The other one you can use Chakalov's theorem. But I think intuitively it should be clear that this is exactly the same. So this is a really sort of brute force convexification. So basically this is, right now this is just notation, but this is going to be useful to think of measures here, because now we can start thinking about what are the moments of this measure, and then we can optimize over moments instead of over points x, and that is going to be, if you truncate it in a correct way, that is going to be a semi-definite program. Okay, so to set up this this moments and the moment hierarchy, we need a little bit of notation. So x to the power alpha is going to be just x1 to the power alpha 1 and then multiplied all the way to xn to the power alpha n. And also of such a, so alpha, we call this an exponent vector, and we use this notation here for just the sum of the entries. So which is of course the degree of the corresponding monomial. Now we define matrices called localizing matrices. So we define m superscript q of mu, and then the entry alpha comma beta. And this is going to be the integral over the semi-algebraic set with integrand x to the alpha plus beta, and then with measure, that's usually the way to think of it, q of x times d mu of x. Yeah, these are called localizing matrices, but for Q is 1, which is sort of the most important matrix. This is called the moment matrix of mu. Yeah, then it's a lemma that if this mu is indeed a probability measure on the semi-algebraic set, actually the only thing you need is that it's a non-negative measure, so really a measure on this set. Then these, as opposed to a signed measure, then these matrices, these localizing matrices, are positive semi-definite. So I think it's helpful to look at the proof of this. So this is an infinite matrix. So by positive semi-definite, we mean exactly this. So for any finite set of exponent vectors and any coefficient vector C, if you take this double sum, then we want this to be non-negative. That's what we mean here by positive semi-definite. And then we just compute this. So we apply the definition, we replace this mq of mu and then the alpha beta entry by this integral. And then there's a summation and an integral, which usually means that you need to exchange these. So we get the integral of the summation, and then we can form a square here in the integrand. And on this set SQ, this measure q of x times d mu of x, this is a non-negative measure, and of course the square is non-negative, so we get a non-negative answer here. So this is indeed positive semi-definite. But now, so this already, I guess, suggests a little bit how you're going to build a semi-definite program. But of course, in a semi-definite program, we want to work with finite matrices. So we need a good way of truncating this. So for this, I want to introduce this vector. So we let y be a real vector that is indexed by the exponent vectors alpha with the sum of the entries of alpha is at most 2t, which corresponds to the degree of the corresponding monomial to be at most 2t. And then this is just a bit of notation. So if you take a polynomial q from our set capital Q, then we write q of x is the sum over gamma, q sub gamma, which is the coefficient, times x to the gamma. Yeah, and now we can, again, we define localizing matrices, but not of the measure mu, but instead of this vector, of this real vector. So how does it work? We use the notation m subscript to t superscript q of y and then the alpha beta entry, and it's this sum. So we sum over gamma, q gamma, and then y of alpha plus beta plus gamma. And this is a finite matrix. So this is only defined for exponent vectors of degree at most t minus the half the degree rounded down. Was there a question or not? Okay. Yeah, and then it's an exercise to show that these definitions that have almost the same notation, right? So let me just really quickly show. So here there was no subscript t, this is not truncated, and this is mq of mu. Here there is a subscript t, this is truncated, and this is mtq of y. And of course, where does this come from? Well, this is exactly right to make the following exercise work. So if we define y to be the moments of mu, so we said y alpha is the integral over the semi-algebraic set of x to the alpha d mu of x. Then these definitions actually agree. So mtq y alpha beta is actually mq of mu alpha beta. Okay, so that's, as I said, many of the exercises here are really to get sort of used to the notation, because sort of, I think what makes these what makes these hierarchies difficult is that there's just a lot of notation, right? So it's good to work that out. Okay, so now we have enough to set up the moment hierarchy. So what do? We minimize sum over alpha p alpha y alpha, which of course, if y alpha corresponds to the moments of a Dirac measure, this is just be evaluated at that point. And then we have normalization conditions, so y0 is 1, that corresponds to mu being a probability measure. And then all the localizing matrices are positive semi-definite, including the special case, the moment matrix for q is equal to 1. yeah, and here the optimization variable is a real vector y, indexed by the exponent vectors alpha of degree at most 2t. Right, and then you can show that this is a semi-definite program. And you can also show that these semi-definite programs, they give lower bounds on the optimal value of our polynomial optimization problem. So if t is large enough, that has to do that if you take t too small, then this doesn't correspond. So for instance, then the objective wouldn't, if t wouldn't be larger than the degree degree of p and then divided by 2 rounded up, then this would no longer correspond to the integral of mu against p, right? So you need to take t large enough for things to actually make sense. And then if you do that, then pt gives a lower bound on the optimal of the polynomial optimization problem. So and the proof is really sort of immediate. So what is a feasible solution of p? So we call p was the minimization of p of x over all x in the semi-algebraic set. So a feasible solution is just a point in the semi-algebraic set. And then we just define y by y alpha is x to the alpha. And if you plug that in, then you will see that it satisfies all the constraints. So it's a relaxation. We sort of throw away constraints. Okay, so let's go back a bit to the sample squares hierarchy that we saw yesterday. So here on top we again have the moment hierarchy. So our polynomial optimization problem was a minimization problem, right? And this is then, we could also call this the primal hierarchy, a hierarchy of relaxation. So each pt gives a lower bound on p. And then what we did yesterday is we dualized, right? So we went from a minimization problem to a maximization problem. And there we took inner approximations of the cone. So which also gives us lower bounds on the optimal value of the polynomial optimization problem. But now my claim is that these are actually, they're both semi-definite programs and they're actually a dual to each other. So showing this is a little bit of technical work. So I'll instead show something slightly weaker, but basically all the ingredients to show that these are STP duals are also in this proof. But I think this is a bit nicer to consider this this proof of weak duality. So what is weak duality? Whenever you have whenever you have an optimization problem and you formulate a dual of it, so here we have PT, we claim that PT SOS is a dual. Then if the primal is a minimization problem, then the dual is a maximization problem that gives us lower bounds, right? And weak duality is just a check that it indeed gives lower bounds. So if you look at the beginning, we start with C, then the end we show what's happening here? This does actually make sense now that I say it like this. So what's going on? So I'm worried about this inequality. This should be the other way around, but where so if anyone sees it, please feel free to help here. What is what is going on here? Why do we have the wrong inequality here? Oh yeah, this actually okay. The first step is wrong, and that's okay. So here I do C P minus C. That doesn't make sense, of course. This should be C C minus P. This should be C minus P. And then everything, all the first terms, they get an extra minus sign. So sorry about that. And then you get a right inequality here. So yeah, so maybe I'm almost inclined to fix this really quickly in the LaTeX. Maybe that's better. So does this make sense? So I made, when I was writing this, I made an error right in the beginning. This should be C minus P. And then here, okay, I'll get to that. So this should be C minus P. So, and what we then really do is we just subtract P and we add P, right? That's all we do in this first equality. So what do we do in the second equality? I wanted to say P minus C lies in the truncated quadratic module. Hence, it can be written as a weighted sums of squares, right? These are the weights, Q of X. And as you saw in the exercise yesterday, a sum of squares polynomial, we can write it like this, where AQ is some positive semidefinite matrix. But now we have C minus P, so there should be minus in front of this, right? So that's this equality. Then again, we have two sums, which basically always means we have to interchange them. So we bring the sum of the Q here, and we bring the sum of alpha inside this trace inner product of matrices. And then there's still minus sign that I didn't write. There should still be a minus sign here. And then what we do is that, okay, this is sort of a complicated step, this last equality. So you have to recognize that this expression here, this expression involving alpha, this is actually, if you take the alpha beta entry of that, so you can work it out, then this is actually the alpha beta entry of this truncated moment matrix. And there's still a minus sign here, which gives us the other inequality. I think we might get a question on it. Oh no, it's just, okay. So I hope that's clear. So I will fix this before uploading the slides. Yeah, and then you can, so this doesn't really prove that these are indeed semi-definite programming duals, but it's sort of very convincing argument, this weak duality, because we prove that they are duals in the sense that weak duality holds. And in this proof, we used all the constraints, right? Actually, this y0 is 1, we used it right in the beginning for this first equality. So yeah, if you can prove weak duality and you use all the constraints, that usually means you have the right dual. But of course, yeah, it's some technical work to really show that these are STP duals, which I will not do here. And then there's actually more. So if S of Q, if the semi-algebraic set is full dimensional, then strong duality also holds. So these optimal values are actually the same. Okay, so now we have two hierarchies of semi-definite programs that give lower bounds on the global minimum of our polynomial optimization problem. So we sort of believe now, without really having seen the full proof, that these are STP duals of each other. So yesterday we saw that this sums of squares hierarchy converges asymptotically to the value we want to compute under the condition that the quadratic module is Archimedean. And for that we used Putiner's theorem. And that means that by duality, you for free you get that this PT also converges asymptotically. But I really want to show how we can prove such a thing. So really just on the primal side. So yeah, here strong duality shows that the moment hierarchy also converges asymptotically under the condition that the quadratic module is Archimedean. And this is because we already know that the sums of squares hierarchy converges by Putiner's theorem. So the question is there a direct proof? And the answer is yes, but it's a proof in two steps. So we're going to show first that PT goes to P infinity. And then we show that P infinity is actually equal to P. So what is P infinity? So let's go back for a second. So here we have this minimization problem with this truncated moment matrix. And this y is a vector on indexed by exponent vectors of degree at most 2t. So if you plug in a t is infinity, this just becomes an infinite matrix, and this positive semidefinite then is exactly what I showed before, defined in terms of such a double sum over finite, over any finite subset of the indices. Yeah, so we're going to show that PT, sorry, still the same problem as yesterday, but so we're going to show that this PT goes to P infinity, and then we're going to show P infinity is equal to P. Just to make sure, we are only considering minimization problems here. So P is a minimization problem, and then the moment problems are relaxations, which are also minimization problems giving lower bounds. So that's good to keep in mind if you work on the proof. So the theorem, if the quadratic module is Archimedean, then we get asymptotic convergence to P infinity. Okay, so fix epsilon greater than 0, and let yt be feasible for the tth moment problem, where, so this is just this sum is just the objective value, right, in this moment hierarchy. So where the objective value is at most pt plus a little bit. So basically the only reason we need to do this, because strictly speaking, we don't know that the minimum is attained. So we need to work with this epsilon. That's just a technicality. So since m of q is Archimedean, so we know that there is a constant c such that c minus the sum of squares is in the quadratic module. So that was an exercise yesterday. And this we can use to deduce the following. So we know that mtq of y is positive semidefinite for all polynomials q. And from this, you get that if we evaluate, so this is basically, we see our moment vector, our y, as a linear functional on polynomials. And then this is going to be non-negative for all polynomials in this truncated quadratic module. So that's something you need to write it out why that is true, but it's not difficult to see. So the moment matrix itself shows you that you're non-negative on squares, and then the localizing matrices actually show you you're non-negative on the full truncated quadratic module. And from this we get, and that's really the important thing in this proof, the Archimedean condition gives us a growth condition on this vectors. So we know from this that yt alpha is at most this constant from the Archimedean condition to the power degree of alpha over 2 times y0, but y0 was just 1, right, with the normalization condition. So I'm not gonna, that's why this, basically why this proof sketch, because I'm not really gonna work this out why this is true. I just want you to see, I sort of want you to believe that it can be true. So one thing you see here, if you know that if you pair y with this polynomial, you get something non-negative. This is going to show that, well, roughly, that y at an exponent vector of a square is roughly at most c squared, right? So this is very vague, but at least I hope you can see why this is going to be true. And then you need to work it out precisely. So first you do it for the squares, and then you use off-diagonal entries of your moment matrix to get it for all alpha. But it's a bit technical and not so interesting. So the interesting thing here is that the Archimedean condition gives us a growth condition on these vectors. And of course, the important thing is this only depends on alpha, does not depend on t, right? And so now we're going to define a linear functional LT on the space of multivariable polynomials. And the important thing is we define it on all polynomials, not on polynomials of up to some degree. And define it as follows. So we just define it by evaluation at monomials, and then you can extend to all polynomials. So at x to the alpha, it is this y alpha t, but then divided by this number. So which means that LT at a monomial is at most 1, right? And then we extend with zeros to the full polynomial ring. So this functional lies in the unit ball. So here I should be precise. What does this mean, unit ball? So we have here the polynomial ring, which you can roughly see as finitely supported sequences, right? So, and on this we just have the Euclidean inner product. And then the dual of that, where the linear functionals live, those are roughly bounded sequences, right? And the dual norm on this is going to be just the supremum norm. And then you see, because of this normalization, this LT lies in the unit ball in this dual norm. And then we know by the Bana-Kaloglu theorem that this unit ball is weak star compact. So it's compact in the dual topology, in the weak star dual topology. So this shows us that this sequence LT is a limit point. So we can go to a subsequence. And thus, if we scale back, and of course using that what we scale by doesn't depend on t, then this yt must also have a limit point, and you can show that this must be feasible, that this is feasible for p. This gives us this inequality. So p infinity is at most whatever the limit is here plus this epsilon. And then, well, we took epsilon arbitrary, so we know that p infinity is at most the limit. Okay, so this is the proof sketch. This is a sketch mainly because I didn't really work this out, right? So now we need to show that p infinity is equal to p, right? So for this, there are many ways of doing that, but I will first show how we can do this using the Ries-Haviland theorem. So this theorem says that if you take a vector y indexed by exponent vectors, and we take some closed set in R to the n, so then there is some finite Borel measure on this closed set K, such that y is the moment sequence of this, the moment vector of this this measure. And this is true if and only if, well, basically pairing this sequence with any polynomial that is non-negative on K gives you a non-negative number. Okay, so how does this work? So if M of Q is Archimedean, then we will show that P infinity is equal to P. So, and we can do this also using Putiner's theorem that we saw yesterday. So if H is non-negative so we want to apply Ries-Haviland. So if H is non-negative on the semi-algebraic set, then H plus So by the way, if you're worried that it's corona, I already had a negative test, so it's just something harmless that I have. So this H plus epsilon is strictly positive on the semi-algebraic set, and so by Putiner's theorem, we know that this lies in the quadratic module, right? So then from the normalization and from the PSD-ness of these matrices, we get, again, as we used before, that pairing it with such a polynomial gives us a non-negative number. But then epsilon is arbitrary, so actually this is non-negative, and we can apply Ries-Haviland. This tells us there's a probability measure supported on the semi-algebraic set, for which you get mu of p is this sum. So you might feel cheated a little bit, because I said we were going to give a different proof. So yesterday we did an asymptotic convergence proof using Putiner, and then by duality we get for free asymptotic convergence of the moment hierarchy. Now I wanted to give you a direct proof, right? But then sort of in the end, it's really sneaky. We're using Putiner anyway, right? So, but actually, if you really want to, you can really give a proof complete. So this Putiner here is really not a very critical way of using it. So you can, if you want to give a proof completely on the moment side. So instead of using Putiner's theorem, you can use the GNS construction and then the Gelfand and Ries representation theorems and give a direct proof that such a measure exists. Okay, so summary so far. Oh, actually, let me skip this. Yeah, Chekhov, that's just to go from the measure back to the original polynomial optimization problem over points in S of Q. Okay, so now we have two hierarchies, two convergence proofs, and now I want to slowly move towards the independent set problem, move back towards the independent set problem, so that tomorrow we can go to point configurations. And basically what I want to do tomorrow is show how techniques you might have seen there, such as the Delsart bound, sort of can be interpreted in this bigger framework of polynomial optimization. Which is just an interpretation, of course. Delsart bounds are much older than these hierarchies. First, but for this we sort of need to strengthen the moment hierarchy a little bit. And so what did we do when we defined these truncated moment matrices? We said we define this matrix only for indices alpha and beta of norm at most t minus this degree over 2 rounded down. Why did we do that? Well, otherwise, sort of this sum doesn't really make sense, right? Because you want, obviously, to sum over all gamma where q has a non-negative coefficient. But then y is only defined for exponent vectors of degree at most 2t. So you sort of need this for this to make sense, right? Oh yeah, that's exactly it. So we need to restrict because otherwise, well, this sum doesn't make sense. So, but now we want to do something else, which might look a bit technical, but actually my claim is that the rest of the results are going to be less technical if you use this definition and are going to be stronger. So instead, we're going to define the partial matrix, which is as big as the moment matrix. So we're going to define it for all alpha beta, where the degrees of alpha and beta are at most d. But it's going to be a partial matrix. So we're only going to set the alpha beta entry equal to the sum if we can actually do that, if the sum actually makes sense. Which, well, I should say if. I guess there are, strictly speaking, more possibilities where this could make sense, but we only want to do it here if the degree of the sum is at most 2t minus the degree. And then this certainly makes sense. And if that's not true, we just leave the entry unspecified. So this is going to be a partial matrix. And now the constraint, so if you say MT of Q of Y is positive semidefinite, that now really means that there is some completion of this matrix for which the matrix becomes positive semidefinite. Yeah, if you think of writing this, so using this new definition of the localizing matrices, there's no problem. The hierarchy is still semidefinite program, because if you write this as semidefinite program, it doesn't matter that you have unspecified entries. Basically, the formulation as an STP is completely ambivalent to this. So this doesn't change anything there. This doesn't matter. And also from sort of an implementation point of view, it's not really true, but sort of the solvers really don't see this as one big STP matrix. They really see a block structure. And what is not really true, but sort of true, is that how difficult it is to solve this matrix depends very strongly on the size of the biggest block. And so what we're doing here, we're just making all blocks as big as the biggest block, right? Which doesn't seem so bad from a computational point of view. But it can, in some cases, give much stronger bounds. And yeah, as my claim would also be that many of the results we use later are actually going to be simpler using this modified definition. Of course, what we lose the duality of the central squares hierarchy if we do this. So we don't have it, we lose that nice duality. So it's okay. So now I want to go to the remaining 10 minutes to first to binary polynomial optimization problems. So where we only care about our variables being equal to 0 or 1. And then I want to specialize further to the independent set problem. So here's an exercise. So what if we have a binary optimization problem? So since we didn't talk about equality constraints, we just talk about inequality constraints. So to model binary polynomial optimization problem, you would add this polynomial and also minus that polynomial to our set Q. And then in the polynomial optimization problem, in the semi-algebraic set, that will force your variables to be either 0 or 1. So the goal of this exercise is to show that if you have these polynomials in your set Q, then you may just as well assume that all the other polynomials are, well, this is sometimes called square free, but that's sort of ambiguous term. So I will say it more explicitly here. So it means that each exponent vector in each term of the remaining polynomials in this set, they lie in this set 0, 1 to the n. So you don't need xi square or xi to the third, etc. in these polynomials. So that's quite immediate, but then what's maybe a little bit more is that you need to show that if y is feasible for the t step in the moment hierarchy, then y alpha is equal to y alpha bar, but alpha bar is obtained from alpha. We're replacing non-zero entries by ones. So it's a bit of a technical thing, but I guess it's useful to do this just to sort of work with the definitions and the notation. And if you do that, you also immediately see that we can write the moment hierarchy in a different way. So what we're going to do now, so there's some notational things going on here. So we're going to index the coefficients of our polynomials because of this condition here by subsets of the numbers 1 up to n. And then this is right. So we sum over all these subsets where p of s is non-zero, and then we take the corresponding monomial, right? We take the product of over I and s of xi. Now the moment matrix, also the notation changes a little bit. Instead of indexing by exponent vectors, we index by subsets. And oh, by the way, I also used the strengthening here that we saw in the previous slide. And then the sum is also a bit different. So instead of using exponent vectors, we use sets and unions. And then, yeah, and also the objective changes. So instead of summing over exponent vectors, we now sum over these sets. So this is going to be very helpful when we go to pointer configuration programs to use this notation already here. But I want to simplify this even a bit further. So, well, I want to simplify it further. First, the specific problem, the independent set problem. So this was the polynomial optimization problem. And well, that's maybe a bit annoying. Now we're maximizing instead of minimizing. So I thought of changing everything in the talk from inf to sub. This is on the weak duality. You should really not do that because you get -1 errors. And also we will look at energy minimization later, and then it's going to be the other way around again. So I thought it's not worthwhile to do that. So this is maximization problem, which means that the moment hierarchies are also maximization problems. And this is what you would get, right? If you would just apply this set Q to the hierarchy on the previous slide. But this is still too complicated. We still want to simplify this more. So namely these localizing conditions, we don't really need them. We can replace them by something simpler. And this is an exercise. So assume that we use the strengthened version of the moment hierarchy. That's important for proving this for t from 1. If you don't assume this strengthening, you can only prove it for t equal to 2 or bigger. Show that we have ys is 0 for all dependent sets. So for all sets that are not independent, right, in the graph. Sets that have 2 vertices that are adjacent. And then what we can do, so we can define a different hierarchy where we kill all these localizing constraints, instead add these constraints, and then, well, that these constraints here are implied by the localizing matrices that's shown in the exercise, and that this still gives upper bounds you can show by a direct proof. Take a feasible vector x and build a y for which this still gives an upper bound. To actually show that these are the same, so this is was done by Monique Laat in her paper in 2001. You need to show the reverse of this, so that if you have the moment constraint, if you have the normalization constraint, if you have the moment constraints, and you have the constraint that y of s is equal to 0 for all dependent sets, then you get the localizing constraints. But that's a little bit more difficult than this exercise. So it's for us, it's not important. You just need to basically need to know that this still gives upper bounds. Okay, so, and this is the, so so for the people who know the del start bound, and I guess we might see it already this afternoon in Henry's lecture. If you know the del start bound, what are you doing there? There are many different formulations, but formulation using Gegenbauer polynomials, you have a conic combination of Gegenbauer, like a non-negative linear combination of Gegenbauer polynomials. You often have some normalization condition, which is here also. You have the condition that these coefficients in front of the Gegenbauer polynomials are non-negative, which sort of is going to, if you plug in t equal to 1, then that's going to correspond to this condition, that the moment matrix is positive semidefinite. And you have some inequalities, right? The function you build using these Gegenbauer polynomials has to be non-positive in a certain interval. And that's going to correspond exactly to y of s being equal to 0 for dependent sets. So you can see it already a little bit how this looks like the del start bound. And of course the catch is that, so tomorrow we are actually going to see how to do that by going from finite graphs to infinite graphs. And then of course the good thing is for t is 1 you get this del start bound, but you can start thinking about what happens if t is bigger, and can we get better bounds in that way. So yeah, tomorrow we adapt this to infinite graphs, and then p of 1 is going to be, p of 1 for the independent set problem is almost the del start bound. So we will also see that. So thank you for your attention.